In this video, we will take a look at this DC-DC step-down buck converter PCB project. It has an integrated synchronous buck converter chip that's rated for up to 24 volts, 24 amps, and you can see it delivering 20 amps of current at 10 volts into my DC load without even a heatsink or proper cooling. If this sounds interesting to you, then keep watching as we quickly run through the hardware design and testing of this PCB project. Let's get started. This video is sponsored by JLCPCB, more on them later in the video. The hero of today's project is Vishay's SIC431 chip. It's a synchronous buck converter with integrated high side and low side MOSFETs power stage, rated for up to 24 amps of continuous current. With a 97% peak efficiency, it has an integrated full protection feature set that include over voltage, under voltage, over current, short circuit, over temperature or thermal shutdown, under voltage lookout with auto retry, and a user programmable soft start. It has a programmable switching frequency of up to 1 MHz, and as you can see here, the efficiency chart looks very great in the 90% range, and the typical application circuit shows that it requires very few external components or passives, while the major part being this power inductor. Just keep in mind that this is a $1.2 chip with minimal BOM requirements. As you can see here on my board, it requires very few passive components for a few cents. Only the power inductor here, this may cost like $2 to $3, and that's all what we need. So we can easily say that this is an extremely cost-efficient integrated solution. And let's now move to our project article. I will leave a link to this article down in the video's description, and let's start designing our schematic. There are two possible ways to go about designing a schematic diagram around this chip. First of which, to use the schematic diagram given in the datasheet typical application. And here we are. The output here is set to 1.2 volts at 24 amps, and the input voltage is expected to be anything in the full operating range. To change the output or to set the desired output, you have to change the value of the feedback resistors network to set your desired output voltage. However, this will also affect the number of capacitors and the value of capacitors for the output, so you will need to recalculate these values and also the power inductor. And if we scroll down here, you will see the output voltage equation that will give you the needed feedback resistor. Just be careful that the low side feedback resistor should not exceed 10 kilo ohm in value. We are talking about this feedback, so you will only need to change this feedback resistor to control the output voltage. And in the same way, you will go about the inductor selection and the output capacitors. The only thing that you can also change here is the mode selection resistors, or mode 1 and or mode 2, and this is done according to the following table. And here are the settings. The mode 1 resistor is used to control the operation mode and also the switching frequency. For my board, I have used this option. I have used a 100 kilo ohm resistor connected to VDD in order to get a switching frequency of 500 kilohertz and to operate in the forced continuous conduction mode. Mode 2 control resistor is used to control the soft start time. You can select between those two values, and the overcurrent protection percentage. You can select the percentage of current that you need. For my board, I have used this mode. I've used 500 kilo ohm resistor connected to VDD in order to get the full current range output of the IC and to have a soft start time of 6 milliseconds. So as you can see, it's pretty easy to configure and adjust this typical application schematic according to your needs. However, there is an even easier way to do it automatically using the Vishay's PowerCAD tool, which is found here. You will click on the Start Your Design, agree to this, and search for our chip, which is SIC431. Click on Design, and here you will enter all of your design parameters, the expected input range for the voltage and the desired output voltage. Let's say we will operate over the full range for the IC with a nominal voltage of 12 volts. Let's say we need an output voltage of 3.3 volts, and the switching frequency, let's leave it at 500 kilohertz. You can change it if you want, and I will set this to the output maximum current. Let's set this to 6 milliseconds of soft start, and the overcurrent protection will trigger at 100% of the valley current in the inductor. This value, I will leave it at 100%. You can change it if you want. I will operate in the continuous conduction mode, and this is good for me. I will create a design. It will take a few seconds to complete, and there we go. As you can see, it has automatically calculated everything that we would need like the output capacitors. We will need 6 of these output capacitors, ceramic capacitors. If you double click the capacitor, it will even give you the part number. The same for the inductor. It gives us the part number for the inductor. As you can see, I can copy this, search for it in JLCPCB library. It's not in stock, but we can look at these parameters of this inductor and search for an identical part. It has also calculated the feedback resistors network. Maybe you will need to verify these mode selection resistors values and connection. However, this is ready to use schematic generated by Vishay's PowerCAD tool. And those are the 2 ways to go about designing a schematic around this chip. And this is what I have done actually. However, I have done 2 more adjustments. Let's take a look at our board here. I have removed one of the feedback resistors and replaced it with this potentiometer to allow myself to control the output voltage. And I did also add a direct connection to the feedback pin using this pin header to allow myself to steer the DC-DC converter using a digital microcontroller, which we will talk about near the end of this video. But everything else is exactly the same as we have seen in the typical application schematic. Regarding the PCB stackup and routing, this is a 6-layer PCB. I couldn't increase the dimensions of this board beyond 50 by 50 millimeters in order to enjoy the offer from JLCPCB that you can find here. Back then when I have designed this board, this offer was only for 6-layer PCB. Now it's up to 8 layers PCB. You will get 5 pieces for $2 if you stick to this dimensions limit. And that's why I have made it 50 by 50 millimeters. Anyway, this space was actually enough to have everything I wanted on the board. If you are going to design a small board like this, I believe you should use an 8-layer board from JLCPCB. It will cost you nothing more. So you will have 2 more copper layers for your power planes. Of course, in a design like this, you cannot use this trace tool to draw the traces for the power path. You should use a power plane like this using the polygon tool and duplicate this power plane in all of your power layers, essentially stacking them on top of each other. And you should use these stitching vias across your power plane, and you are up to the races. Now you can deliver insane amounts of current through your board. And at this point, we can move to the next step, which is manufacturing the actual board. We will export all of the fabrication files needed by JLCPCB and go to their website. And now this is our sponsor time. JLCPCB is one of the largest PCB manufacturers in China. They offer amazing quality services for affordable and competitive prices. You can get up to 4 layers PCB, 5 pieces for only $2. This is 10 by 10 centimeters, and up to 8 layers for 5 by 5 centimeters PCB for only $2 as well. They also offer flexible PCBs, very affordable PCB assembly service with a huge stock of parts that you can get for very affordable prices as well. They also have a high quality 3D printing service and CNC machining service, and a huge stock of mechanical parts that you can use for your projects. Register for a new account using the link in my description and you will get a $60 discount coupon that you can use for your projects. After uploading my Gerber file, I had to also upload the BOM file and component positions file, place the order and wait for the PCB delivery. And here is how it looked after I got it from JLCPCB. Now let's move to the test bench and start testing our board. I have soldered in this potentiometer and these connectors. These connectors are rated for up to 15 amps of current per pin, and that's why we are using 2 pins per power rail. Before taking any measurements, let me explain what's going on here. Here is our board under test. This power supply is the main source for power going into my buck converter board. So it's connected to the V input of the regulator. The output of the regulator is connected to the DC load, channel number 1, which is rated for up to 200 watts. So we can push up to 200 watts of power into this DC load. In a multi-channel DC load like this, you can connect both channels in parallel and run in CC mode, and you will have double the power capacity. This multimeter here is used to measure the input voltage at the input terminal of the regulator, because there will be some voltage drops in these cables running from the power supply. So the voltage seen by the power supply will drop by a little bit when it reaches here into the input of the buck converter. So I'm taking the input voltage measurement from this multimeter, not from the power supply itself. And the same for the output voltage. The output voltage going into the DC load is not exactly what's at the output capacitor. So I'm measuring the output voltage from the output capacitor using this HP multimeter. The scope here is connected to the output power line to check the ripple voltage. This is a bit tricky measurement to do it correctly. I'm not saying that this is the most accurate way to measure the ripple, but we will have something to look at. But it's not the most accurate way to do it. When we turn on our buck converter regulator, let's say the voltage will go from 0 volts up to 5 volts. If you zoom in here at this 5 volts power, you will find that it's actually fluctuating, and this is probably the 500 kilohertz switching frequency from the buck converter itself, and we need to measure this peak-to-peak voltage ripple. To achieve this zooming, we can actually increase the voltage scaling from the scope. However, the dynamic range for any scope is typically limited, so we can't use this in a practical way. We can instead AC couple our voltage. Instead of being DC coupled, it will now be AC coupled using the internal capacitor of the scope itself. And now we can increase the voltage scaling to have better visibility for the V ripple. But of course, there will be some inaccuracies due to the internal capacitor from the scope itself, the bandwidth, and of course the grounding here for the scope probe. Anyway, the last measurement that we need also to take is the temperature. In each test case, I will let it run for a few minutes, then I will take the temperature measurement for the IC itself. Now the ambient temperature is about 28 degrees Celsius, and let's turn on our power supply. Here you can see that the output is set to 5 volts at the output, and the input is 12 volts. The DC load is running in the constant current mode. It's set to 1 amp. Let me enable the DC load. And now we have 1 amp of current flowing into the DC load. Let me disable this. Let's increase the DC load current maybe at 8 amps. Let's take a measurement at 8 amps of current flowing into the DC load. I will enable the load, and now we have 8 amps of current into our DC load. The output here is 4.99 multiplied by the current, which is 8 amps. This is the output. And for the input power, we have 11.25 multiplied by the current of the power supply, which is 3.68. So the efficiency here is 96.4%. Using this potentiometer, I can easily adjust the output voltage. Let me set it to 3.3 volts. You can observe the output voltage here. And there we have a 3.3 output voltage, and we can also test this operating point. However, this will take a lot of time. I have done all of these measurements. Let me go to the PC and show you the results for all of these measurements. In this test case, we have a 12 volts input from the supply, and the output is set to 3.3 volts, and the output current going to the DC load is 1 amp. So the efficiency will come out like this. The output voltage is 3.28 multiplied by 1 amp of current. This is the output, and the input voltage is 11.94. We are taking the measurement for the V input using this multimeter, not from the power supply itself. Keep this in mind. And the current is 0.3, so the efficiency will come out like 91.5%. This is under light load. We are measuring a load of 1 amp. Let's increase the load up to 10 amps, and it will become like this. The output is 3.27, and the current going into the DC load is now 10 amps. Let's check the efficiency. It will be 94.7%, which is very good. Next up, we have the same input voltage, 12 volts, but this time the output is set to 5 volts, and the load is light load. It's 1 amp of current, and in this test case, the efficiency will come out like 91.6%. Increasing the load current to 10 amps under the same voltage conditions for the input and output. Now we have an efficiency of 95.8%. And now let's increase the input voltage going to the DC-DC buck converter. 24 volts is the maximum value that we can put here on the V input line. This test is under light load. The load is set to 1 amp and the output is set to 12 volts. Our converter is regulating the 24 volts input down to 12 volts output at a light load of 1 amp. These numbers will give us an efficiency of 80%. Increasing the load up to 10 amps of current. Now the output is 12 volts, 10 amps, and the input is kept the same. Now the efficiency will jump up to 95.8%. For the last test case, I will keep the input voltage at 24 volts, which is the maximum value that we can have, and I will try to reach the limit of my power supply, which is 10 amps of current. So I had to set the output voltage to be 10 volts. as you can see here. Now I'm regulating 24 volts input to down to 10 volts, and the output current is 20 amps, as you can see here. Under these conditions, the efficiency came out to be 94.2%. The reason behind this test case is to try to get very close to the maximum current limit for this chip, which is 24 amps. Now we are running at 20 amps, and after letting it run for a few minutes, the cables I'm using started to get very hot, so I had to stop the test and take the temperature measurement for the IC, which was very close to 85 to 90 degrees Celsius, which is half what it's rated for. This chip can run up to 150 degrees Celsius. And this is without a heatsink or any sort of cooling. Before concluding this project, let's take some notes. First of which is the output voltage. In most cases, I think you are going to use this chip to generate a fixed output voltage. And in that case, you need to use very small resistors and place them very close to the feedback pin. If you want to have an adjustable voltage, you can use an SMD potentiometer and place it very close here to the feedback pin. A smaller package will be much better than what I have done here. This kind of setup introduces a lot of noise to the feedback line. You can also use this chip maybe for battery chargers or something. For a battery charger application, you may need to change this R1 resistor into this array of resistors with different values to give you different voltages. 10 volts, 12 volts, 14.4, whatever you want, and use an analog switch or whatever to switch between the high side resistors and keep the low side resistor at 10K. This is one way to do it. This was the first point. The second point is this steering input here. As you have seen, I had to manually play with this potentiometer to change the output voltage. However, we can do it digitally. We can do this using a microcontroller. Like in digital power supplies, you use a digital interface to control the output voltage. One way to do it is to use a current output DAC to source or sink current into this feedback node to deceive the buck converter into thinking that the output voltage has changed. So it's going to change the drive signals to change the V output voltage to bring down the V at the feedback pin down to 0.6 volts, which is the reference voltage. And now by sourcing or sinking current from this node, we can control the output voltage. Typically, the built-in DAC in any microcontroller has an output voltage. We can use an external buffer with a resistor like this R3, and now we have a current output DAC. But of course, you need to figure out the optimal operating point to select these R1 and R2 resistors and also R3. You will find a lot of information online about this and equations to find these resistor values, and you can also run some simulations to do it. I have done that before. All what I can say is that it's a very tricky business to do. You need also to consider when the system is powered up for the first time, what is the voltage is going to be here, what is the voltage that will be here, because it may shoot up to the maximum value. The V output, it may behave uncontrollably. Non-careful playing with this feedback pin can and will drive your regulator out of control. But of course, this setup will actually work if done correctly. And now let's move to the final point. And the last note is about the limitations of this IC. Most probably you'll notice that the input voltage range is not very wide, or it's not wide enough for many applications. However, it's still sufficient for so many applications. But of course, you may be limited by this 24 volts input. One other limitation may be the adjustability of the output voltage. As I have just shown you here, that it's not very easy to do. And this is compared to the Vishay's SIC 45 series, which offers up to 40 amps of current with integrated controller. Now you have an integrated controller here to control the output voltage with a resolution of 2 millivolts. This chip has a higher peak efficiency, and it can be controlled using I2C power management bus. It is supported, so you can use your microcontroller to control the output voltage easily, and it does also support remote voltage sensing, so you can sense the voltage at the terminals of the output. In our last measurement, the output was set to 10 volts. However, what was seen by the DC load was 9 volts. There is a 1 volt drop here in these cables due to the high current, which is 20 amps. Now, if you are using the SIC 45 series, you will have a sense cables to connect them directly to your load. So it will adjust the output voltage to accommodate for the losses in the cables, and now you will have 10 volts seen by the load, which is a very good feature to have actually. I think I'm going to use this chip for a future project. Please leave a comment if you want to see this chip in action. And as you can see, nothing is perfect. This chip has more limitation for the input voltage range. It goes up to 20 volts only compared to our 24 volts buck converter that we have seen in this project. And this concludes our project. Please consider liking this video if you do like it, and subscribe to the channel to not miss any of the upcoming videos. I'm signing out, and I will catch you in the next one.